I would like to introduce Dr. Julie Robinson. She is the Human Exploration and Operations Mission Directorate Chief Scientist and Manager for Science and Technology Utilization at NASA headquarters. And she is going to be giving us a talk on Artemis, Gateway, Lunar Surface, and Orion. So welcome, Julie.
No, thanks so much, Kevin. Thanks for the invitation. So in my presentation today, I'm going to go over very briefly four main topics. First, what is our Artemis strategy and plan for human exploration? Then what's the strategic value, or how does physical science fit in that strategy? And what overall capabilities for physical sciences might come from the architecture? And then finally, how HEO is working with STMD and SMD jointly to ensure that those capabilities are available as the lunar architecture develops. And as you might expect, that's going to be a process, not a single event. So first of all, our first mission to land on the moon, even though that's something we did decades ago, and I'm on page 3, Lisa, thank you. We are doing it with all new systems and a huge amount of additional knowledge about how to best support the human body in space missions. So what you'll see first, of course, is we have precursor missions that the Science Mission Directorate's doing. The Lunar Reconnaissance Orbiter is giving us all kinds of information about the ground, the early South Pole robotic landings, Viper coming in. What's going to happen for the human missions is we'll have Artemis, which is our Artemis 1, which will be our first time to send a human spacecraft to the moon in the 21st century, but that will be uncrewed. Then Artemis 2 will have crew on board, but they will not land. They'll go into the near rectilinear halo orbit, which is the first time we'll have used that orbit in human spaceflight. Then along the way, we'll get to Artemis 3, which is our first deep space crewed mission, our first lunar landing of 2 crew members on the surface. And the Gateway will begin its development and operations with the launch of the power and propulsion element and the halo, or the habitation and logistics element. Gateway is very small. I think of it almost like a changing room. It lets us make different components reusable in orbit over the longer term of the architecture. If we could go to the next chart. So after we get those first missions under our belt, we move to the buildup of the Artemis base camp. And this is our approach to a sustainable presence on lunar orbit, in the same way that we want a sustainable presence in low Earth orbit. So we want a sustainable presence in lunar orbit and on the surface. So we expect to gradually have a buildup of different components that support the crew, such as the lunar terrain vehicle to allow them more mobility to get to more science sites of interest. Then eventually, as we have more and more crew landers, we'll have a pressurized rover. On the technology side, there'll be a fission surface power plant as well as an ISRU pilot plant that are deployed. And then finally, we get to a surface habitat so that we can finally have 4 crew members live and work on the surface. Next chart, please. So this chart is a Science Mission Directorate chart on the kind of top 7 strategic science objectives for Artemis, but I annotated it in blue and yellow just to kind of show where physical sciences lives, conducting experimental science in the lunar environment, and investigating and mitigating exploration risks. And also where technology development lives, because many times the physical sciences and our understanding of different processes in the space environment really comes from the physical sciences, then it crosses into engineering and technology development. Next chart. One important thing to think about from a human exploration perspective is, in what ways is the lunar surface and the Mars surface, are they analogs for each other? Because much of what we're doing in our architecture is aimed at having multi-purpose facilities. So as we test a mobility platform for the crew on the lunar surface, we want that to teach us and to establish the parameters for a mobility platform that would be used on the surface of Mars. So in these environments, we have the same altered gravity, but of course it's 1/6 Earth gravity on the lunar surface, 3/8 on the Mars surface. Radiation is similar with both galactic cosmic rays and then solar particle events, which you can shield for. In a hostile closed environment perspective, we're in a different atmosphere. We're expecting to use an exploration atmosphere with a lower total pressure and enriched oxygen compared to what we're doing on ISS today. Also, those environments have dust, although the lunar dust and Mars dust are quite different. From a distance from Earth perspective, on the moon, we still have relatively fast communications and a return maybe 2 to 3 days, but practically from near halo orbit, closer to a week to return from the surface. So we can come home if we have problems, better than a Mars mission where we really have to do the full round trip and it could be 9 months return. We also don't have the comm delay. So that makes the moon a perfect place to test technologies and autonomy for Mars forward exploration purposes. And then finally, from an isolation and confinement perspective, we're dealing with missions and we can design our missions to be very predictive of what it would be like for the crew to live and work on the Mars surface. Next chart. So we can also think of early mission operations with very limited resources and support as analogs for the first Mars landing. Over time, we'll extend the duration and the infrastructure till we get to longer missions on the surface, but we can also do combination missions with the crew staying at the gateway, especially in something called the transit habitat, which would both be tested at the gateway and then turn around, put on a propulsion module, and used as the crew habitat for the transit to Mars. And so we have the ability to do some combination test missions before we make that first Mars transit and prove out that transit habitat, which is a really important opportunity in the architecture. Next chart. So overall, these lunar missions prepare us for Mars in many ways. In orbit, we have deep space aggregation, we have the Mars transit habitat, orbit to surface operations, commercial resupply and refueling, which is particularly important, and using it as a crew health and performance analog. On the surface, we're testing our spacesuit advancements, our mobile operations and approaches, planetary protection needs, how to work between humans and robots and seamlessly combine those together to optimize science return. And we're learning how humans are resilient as they work and live in these challenging environments. So as much as possible, our lunar systems are designed for dual Moon-Mars operations. Next chart. And so just to kind of summarize the matches, the similarities and the differences, you've got a similarity in gravity. It's close for partial gravity. You've also got a microgravity opportunity. You've got a match for the environment. You've got a match for radiation as deep space radiation, depending on your duration. The early short missions, even though it's deep space radiation, may not have that significant a radiation exposure. You've got a match for isolation and confinement, depending on the duration, but you're less connected in a Mars mission than you would be in this lunar mission. So that lets you test new systems. Next. So working with people like Fran Chiaramani and Kevin Sato, one of the things we tried to envision is how do you think about cross-platform research strategy? Because for the first time in history, we will have both a low Earth orbit platform as well as lunar platforms operating at the same time. That offers really significant cross-platform opportunities for things like dust mitigation, where you can study microgravity, but then you can study partial gravity environments. For cryogenic storage, chill down and tank transfer is another really important area with the ability to do, say, fluids transfers on ISS to understand how you would load vehicles with liquid propellant before they would go to Mars. Then the ability to look at landers and surface storage of cryo and do that on the lunar surface, predictive for the way that those materials would behave on Mars. Flammability is really interesting because not only do you have the microgravity combustion differences with Earth combustion, but also the fact that we'll be in an enriched oxygen environment compared to what we've been used to operating in on the ISS. And so having combustion models that can both look at atmosphere as well as partial gravity, that's a really important area that has not been well investigated in the past. But it may be that drop towers are the most efficient way to get a large amount of data early on. Next chart. In the area of regolith extraction and solidification, really understanding and demonstrating how you do that, and pairing that with the science observations of what actually is in these minerals, how much water is there, how would you extract it, and so forth, is an important line of research. And then materials performance in general, how materials are performing in deep space radiation, thermal, and dusty environments. And all of those things are very enabled by measurements such as dust samples or regolith samples that will come from the science side of the house. And so combining these, or working with planetary sciences and working with space technology, is a really important way to make some of these advances have the most relevance. Next chart. And similarly, our crew health and performance system itself rolls many of these together into engineering systems that are designed to keep the crew healthy. So I just wanted to put that chart up briefly to mention that these things all come together in systems that will support the crew on that first mission to Mars. Next chart. So the first crewed landing, it's going to be the crew members living in the landing system cabin for 6.5 days on the lunar surface. They'll do up to 4 moonwalks. They'll deploy instruments. They'll collect a variety of geologic samples to return to Earth for later research. And they will capture the real-time human response measures and environmental characterizations that help us start understanding how this environment affects the crew. And they'll do that with a limited and shared sample up mass and down mass. Next chart.
There's someone with a hot mic. Can you please mute yourself? Thank you.
Thanks, Kevin. There are some early Gateway science payloads that will be on the small beginnings of the Gateway. URSA is a European Space Agency radiation instrument package, takes advantage of the Gateway's unique NRHO orbit. Hermes is a NASA space weather instrument to observe solar particles and solar wind. And then ESA will have an internal dosimeter array inside the halo that will include instruments provided by the Japanese Space Agency. Next chart. And then the human landing system is a brand new commercial procurement of a lander for the moon to help us accomplish all of these things over time. It will carry the crew to the lunar surface and return them to lunar orbit. Then Orion will bring them back home from there. It serves as the habitat on the lunar surface for the early missions until we get a habitat element on the surface. And it will house equipment for the surface activities, including things they need for the moonwalks, the sample collection, and scientific experiments. Next chart. That landing system, you may have seen, has been in the news because we've been procuring that initial human landing system for a no earlier than 2024 launch date. And we've been through that announcement in the 2020s in spite of the pandemic. In July, this chart isn't quite up to date. In July of 2021, we did announce the selection of our HLS provider, our Option A contract award, and that was announced to be SpaceX. Blue Origin, one of the competitors, has the protests have been resolved now, but they did file with the Court of Federal Claims just this week on August 13th, or just last week. So there are still procurement challenges going on there, but even so, we're moving forward on implementing and having that HLS lander as soon as we possibly can. At the same time, we're getting ready to go out with something called the Lunar Exploration Transportation Services contract. That's called LETS. The RFI went out on the street in July of 2021. And what this will do is procure the future landers. So this first lander is just one. NASA would love to have it be one of many, and NASA be one of multiple customers for these landers. That helps enable a broader economic ecosystem on the moon. Next chart. And the Artemis Base Camp is a huge enabler because this is where science, human exploration operations, and space technology can all come together. This is where we can prove out our EVA suits, our approaches to mobility, our the ways that we would live and work on the surface of a planetary body, whether that's the moon or Mars, power systems, communication systems, navigation systems, and how we would use resources to extend and expand that human presence and that infrastructure overall. So the Artemis Base Camp is really important for that goal of sustained lunar presence. That is one of the American strategic goals for Artemis and our return to the moon. Next chart. So how do we work together between HEO, SMD, and STMD? Well, we track the goals and objectives of all three mission directorates, and we keep those that are applicable to human missions in a plan that we're developing right now. I wanted to share with you some of the cornerstone capabilities for utilization that we're developing, because these are the equivalent of facilities, if you will, from the ISS system. These are the things that the architecture components need to work together to enable for us to do some of the best science. So some of those things that we're working on are access to and operations in new terrain. These are our traverse use cases that help inform our crew and rover mobility and our communications. We're working on sampling, curation, and transport strategy. Orion is very limited, and we know we need more than that over the long term, so we need to define requirements for core tube samples, stratigraphy, identifying collecting rocks, what we'll do with how we'll handle biological samples, cold sample curation, documentation tools, and the entire system for how we would use all of these different elements to bring samples home. Planetary protection strategy and microbial monitoring is another area. Extended duration orbit and surface missions for experiments and technology development, and that includes both ISS and Artemis. Integrating and coordinating access to human test subjects pre and post-flight. The uncrewed and robotic rover operations for utilization. So just because the LTV was put on the surface for human mobility doesn't mean that the rest of the year it could not be used for science. So working out how we would define those requirements and how we would use the systems together to optimize return and to optimize the science value. The instrumentation and measurements that we would make on the surface, and how we would do complex operations in permanently shadowed terrain in cold regions. So the PSRs are one of the reasons that we're going to the South Pole, because that's where it's likely that permanently frozen water ice or CO2 or other components would be available. Those are also incredibly cold places to operate, and we don't know a lot about them yet. Viper will be an important precursor mission. We don't even know for sure in some of these areas if we could safely drill at those temperatures and collect a sample without releasing the volatiles. So there's a lot of work to be done there for enabling the overall utilization.
2 minutes, Julie.
Thanks. Next chart, and this is my last chart. There are a couple of documents out there that tell you at a high level what the Artemis plan is. There's a NASA's plan for sustained lunar exploration and development from April of 2020, as well as the Artemis plan from September of 2020. So I urge you to go take a look at those. They kind of lay out the philosophy I just shared with you at a high level. And there's a lot of work going on. I just briefed the BPS Decadal Committee this week as we try to connect and help them stay up to date, because these things are changing very rapidly as our schedules change, as we start putting things on contract. They may look different than the government models you see here. And so there's a lot of dynamic change going on as we start standing up a real Artemis program and making very firm plans to go to the moon. So I'm happy to take any questions. Thank you.
Great. Thank you, Julie. That was wonderful. We do have time for a couple of questions. We do have one question, if I can see it, find it again in the chat from Michael Fisk. What is your estimate of a surface settlement selection date and the time frame between location selection and the first surface habitat at that location?
So I think it's really important to separate the base camp from a settlement. So the base camp is a place that you could go for up to 30 or maybe 60 days, but having people live on the moon permanently for year after year, like they have done on ISS, is much further out there in the architecture, because this is a very challenging place to live. We have a lot to learn from shorter missions, in the same way that we needed a lot of shuttle missions to learn about 2-week to 30-day responses to microgravity before we could have crew members live on ISS for 4 months, and then we got it to 6 months, and now we've had a handful of people at 12 months. So there definitely needs to be a buildup, both of the infrastructure as well as the knowledge, before you get to a permanent settlement. But the Artemis Base Camp itself, we expect to have that coming in as early as possible in the architecture. That depends on a lot of things. For example, even though we're awarding an HLS contractor for the first landing, they don't actually have that spacecraft built yet. So there are going to be a number of things that affect that final manifest schedule. But certainly by the end of the 2020s, we're hoping that we would start having at least components of that base camp infrastructure on the surface.
Great. Thank you. And we also have a question from Chris Salvino. If he'd kind of like your thoughts on the landing date of 2024, and if that's still something that we are targeting, or what your thoughts are.
Yeah, on this, I'll just quote some of the words of our Administrator Senator Nelson. He said publicly that, we set dates and we challenge ourselves. These are very hard dates. So everything that happens along the way, whether that's a challenge in an engineering solution or whether it's a challenge like contracting, is likely to slow that down. So, I think you have to watch and see what happens. It's probably not early 2024, certainly, but along the way, there'll be good reasons for the changes that occur.
All right, well, great. Thanks, Julie.